My name is Terrell. I'm the lead for the air conditioner experiment, so that's what we're talking about today. So in general, I'm just going to talk a little bit about the theory behind refrigeration cycle and heat pump, and we'll look at some diagrams, and then do some coefficient of performance calculations, and just kind of compare the refrigeration cycle and the Carnot cycle, with a little bit of analysis, and then go over a conclusion. So what we're using, so a refrigerator or an air conditioner, basically the same thing, is just a heat pump. And the main purpose of a heat pump is to move heat from one place, from a low temperature reservoir to a high temperature reservoir, or backward if you're trying to cool something. And so, in general, what you're normally looking at with thermodynamic cycles is that you're putting in heat to get work out, but with a refrigerator or an air conditioner, you're putting in work to remove heat from a system to cool, make your house or whatever. So here's just a general diagram, and you can see the main components are the compressor, condenser, evaporator, and the expansion valve. And so the heat exchange takes place as air in whatever space you're trying to cool is blown across the cool air after it leaves the expansion valve and goes into the evaporator. And so these are the cycles that we've probably all seen before. So you can see that the compression of vapor, there's isentropic compression of vapor, and then constant pressure, phase change, and then there's temperature decrease across the expansion valve. And then the liquid is converted back into vapor. And then this is just a pressure enthalpy diagram to kind of give an idea of how the work takes place in the cycle. And then so that's the same temperature entropy diagram on the right. And then this is compared to the Carnot cycle. So the Carnot, or if you turn the Carnot cycle around, it would match the refrigeration cycle more. So you can see that the Carnot cycle is a little bit more efficient because it's a square here, but then over there, if you don't go into the superheated region, there's a portion that you're losing for the heat that you can take out. And then that's going to be, or the difference in efficiency or coefficient of performance is reflected when you look at some of the calculations. So the coefficient of performance is similar to an efficiency. It's kind of conceptually the same thing, but efficiency is always less than 1. So the coefficient of performance is the heat divided by the work you put in, and then for a Carnot cycle, it's the low temperature divided by the temperature difference. And so they gave some values in the lab manual. So I calculated the Carnot cycle coefficient of performance, and I came up with pretty much all the same numbers that Blake did when I went through it. And so what you get for the Carnot is 10.8, which seems high, but Carnot is the ideal case, which is the sort of limiting from those thermodynamic cycles. And the highest possible value for refrigeration cycles I've read is around 8. And the best, that would be for like an ideal refrigeration cycle. The best real systems are much lower, around 4 or 5, and then the ones that you normally see, average ones, are the one we're going to use, probably you can expect to be around 3 coefficient performance. And so, basically in general, an air conditioner is just a reverse heat pump, and we use work to remove heat in order to cool space. And you can sort of quantify that with the coefficient of performance. And as you could expect, the cycle's not going to be ideal, so that's why we're going to test it. A few things to look into is how the charge, the freon, affects the coefficient of performance. Hopefully it doesn't break. That'd be ideal also. Any questions?
How can you have coefficients of performance greater than 1?
Well, so efficiencies always have to be less than 1, but a coefficient of performance is heat divided by work, whereas an efficiency is work divided by heat. So it's kind of like a reciprocal.
So what's the difference, or like, what do you think the differences are between like the actual physical system where like a coefficient of performance is 3 compared to one where it's like 4 or 5?
I think in general, probably a lot of it depends on the actual like physical parts of the system and how well heat exchange can take place and how much loss you have, especially in the evaporator and the expansion valve, and just the efficiencies of the compressors and the parts. My assumption.
Good presentation.
Any other questions?